All right, we have the classic monkey and banana problem. Let me set this up for you as to what's going on in this problem. I have it all pre-drawn. It's in your book on page 103, sample problem 2E. What we have is an escaped monkey from a zoo that goes up a light pole and hangs on up here 5 meters off the ground. Zookeeper with a tranquilizer dart gun takes a shot at the monkey along this hypotenuse here at a certain angle that we don't know yet. The gun barrel is 1 meter off the ground. That's the point of the red line. And the zookeeper is 10 meters away from the monkey's light pole. What we want to know, and the question also states that the monkey tries to trick the zookeeper by dropping a banana. Now, it doesn't say where the monkey is holding the banana, but I think we have to assume that the zookeeper aims at maybe the chest of the monkey, and the monkey has the banana around its chest. So as soon as, like the split second that the zookeeper fires the dart, the monkey drops the banana, and the question says, does the dart hit the monkey, the banana, or miss both? And this is quite an interesting problem, and let's dive through it one little section at a time. The first thing we're going to do is solve for angle theta. We need to know what angle this is. So on this layer, I'm just going to look at the triangle that is here. So this triangle right here. And it's going to be 10 meters this way, 4 meters this way, 4 meters. And to find that would be tangent. So we could say the tangent of angle theta is 4/10. And so that would be second tangent 4 divided by 10 equals, and theta would be something around 21.8 degrees. Now, you don't want to go rounding crazy here, because this problem's answer is depending on accuracy. So you want to go out a few decimal places whenever you can, but 21.8 is what the book and I both use on this one. All right, now we're going to find the time it takes the dart to go to the monkey. All right, so let me introduce a couple formulas here, and this will all work out to find the time. And this is going to be a pretty speedy explanation of this. If we say the velocity in the x direction equals delta x over t, and we solve for delta x, well, delta x would be v sub x times t. We don't really need the dot, but I'll put the dot in there. Now, the way that you would find the velocity in the x direction would be very quickly here is to look at this triangle with this being your speed vector. Okay, this way, that's the dart speed. And this is 21.8 degrees. We just found that here. To figure out v sub x would be this side right here. All right, so very quickly, this would be the cosine of 21.8. 21.8 would equal v, I'm going to run out of space, vx over 50. There we go. And so to solve for vx, we've done this a billion times, is 50 times the cosine of 21.8. All right? And that works out to be about 46.4 meters per second. Okay? 46.4 meters per second. Now be careful where you go labeling that, because if I start writing 46.4 all over my triangle, it's going to be a big old mess. So I want to really be careful what you write, unless you're going to redraw this a few times, which probably wouldn't be a bad idea. There's a problem not a problem, a formula that looks like this though. It says delta x equals vi cosine theta times the time. And we can use this to find the time. And what I want to really drive home here is what's in this blue circle, I'm circling right there, is the same thing as this right here. Because to solve for Vx, you have to take 50 times the cosine of 21.8. And when I plug in what I know all of this stuff except for t. All right, let's do the right side of this first. The initial velocity of the dart is right here, 50 meters per second. So that's 50 times, just for the sake of clutter, I'm going to leave the units off, times the cosine of theta, and we know that that's 21.8 times the time. So that's the right side, and the left side is delta x, and delta x is 10 meters. This is delta x. Okay, so this is 10 meters, and if we solve all this, okay, this would be something like 10 equals, and this would be the answer of 50 times the cosine of 21.8. It's 46.4. Again, I'm kind of rolling through this, and then you would solve, so we would divide 46.4, and the time equals 0.215 seconds. All right, the next thing we need to do is figure out info on the banana. So we're just going to make a mental note, because I'm going to take this off, that the time was 0.215 seconds. All right, so now on this slide, we're going to deal with the banana. So let's get a banana color here. There we go. Banana. And this banana is being dropped, and whenever something is being dropped, we have our delta y formula of 1/2 gt squared, where that's going to be, the time is going to determine that. So we're going to figure out its position, and that's 1/2 times negative 9.81 meters per second squared times our time of 0.215 seconds from before, and that is squared. Now, when you do this, when you take 0.215, square it, and times it by this, you're going to wind up getting something like negative 0. And that's negative 227 meters. In other words, from the monkey's hand, this thing fell 0.227 meters. So probably about like, how long is that? I don't know, a few inches. It's not very far. Not very far. I'm not going to convert it now, as I'm running out of time. But this banana just barely falls like this. So this is a super important piece of information. I'll circle that because we'll be coming back to that. Now, let's deal with the dart. We'll get a dart color. It's a little bit greener. For the dart position, we got yet another formula. Okay? And it looks like this. Delta y equals vi sine theta t. That's times t. So it's vi times sine theta times time minus 1/2 gt squared. What a nasty looking thing that is. Now let me show you what that means. Okay? Let's make the path of the dart white so it sticks out. Where did my white color go? There we go. Okay? This dart isn't going to hit right here. It's going to come up kind of like this and drop off a little bit because gravity is going to be pulling it. Now, when you go kick a football, that football hits the ground. It doesn't continue up in a straight line. It starts falling immediately. So depending on the speed and things is determined by how fast this thing's going to, or how far it's going to fall down. Well, this formula here tells you the vertical position of the dart over that time interval. And the way that you would do this, so it's going to take where it should be and also subtract the falling part. Now you can see that this right here, that is going to be the same as this answer. Okay? So if we start plugging stuff in here, delta y equals vi, which is 50, times, that's the dart velocity, times the sine of t. Now remember, the sine is the opposite side, and you can explore that on your own, but that's why they use that trig function, because it's the opposite side. So it's 50 times the sine of theta, so that would be sine 21.88 times the time interval. Put these in parentheses. The time interval is 0.215 seconds. And we're going to take away from it the answer to this problem up here, so I won't have to redo that again. 2.227. 0.227. Well, when you do 50 times the sine of 21.8 times 0.215, you will get something like 3.99. Okay? And if we take away 0.227 from it, and by the way, we're keeping this value that we plugged in here positive, even though that's a negative answer, because we're looking at it from the monkey's perspective. So this delta y would be, because it's falling down, would be 3.765. All right, and that's meters. What that means is this monkey is 4 meters up from here to here. Well, the banana only falls 0.227 meters, which is like, let's say it's right there. That's exaggerating a lot. It would be way less than that. The dart happens to hit 3.76 meters up the pole out of 4. So if this dart didn't drop at all, it would hit 4 meters. But since it dropped a little bit, it hits slightly down. So it hits 3.76 meters up the pole. So up this way. 3.76 meters up. That's what this answer means. A lot of people get that mixed up there. And so the question asks you, does it hit the light pole, or does it hit the monkey or the banana? And you can actually see that due to its position, the dart position, and where the banana actually fell, that it would actually hit the banana, because the banana, let me get a new graph here. Okay, let's look at it this way. The banana falls 0.227 meters. The dart hits up 3.765 meters, and this is all in relation to the gun barrel here. We're not even really worried about that distance right there at all. But if basically if you add these two together, that's 4 meters. So in relation to where this thing dropped and this bullet fell is the same distance, because they were fired at the same time. So it would hit the banana. We would have a banana falling, tranquilizer dart stuck in it, like that. All right, and have a good one.